Carson is an adjunct professor of engineering at Seattle Pacific University and affiliate assistant professor in industrial and systems engineering at the University of Washington, a fellow of International Council on Systems Engineering, and an INCOSE certified expert systems engineering professional. That's a lot. That's awesome. Dr. Carson provides consulting services as required in systems engineering methodology and training, especially in requirements, development, validation, and systems engineering measurements. Dr. Carson also has a PhD from the University of Washington, nuclear engineering, experimental plasma physics, and a bachelor's from California Institute of Technology in applied physics. His current focus is on incorporating sustainability considerations in systems engineering methodologies and education. We have a link to his LinkedIn profile. Feel free to connect. Also, the presentation link is at the bottom of this slide here. So without any further delay, Dr. Carson, I will let you take over. Thank you so much for being here with us.
Thank you. My pleasure. And I so appreciate the people calling in from around the world. You have set very high expectations for me. So I appreciate those who've gotten up early and those who are staying up late. Did you enable me to share?
Yes.
I tried sharing. There we go. Thank you. And where is there it is. All right. Let me get myself arranged here. All right. So this is a presentation I actually gave last fall at the WSRC, Western States Regional Conference, but by special request, I'm here again, and the number of people is overwhelming. So thank you very much. This is going to be very quickly moving, but we have time at the end for questions. So I want to talk with you about how to use the architecture in an MBSE tool to develop validated requirements. The first version of this actually started in 2019 at the International Symposium with a lightning round presentation, and that's available on YouTube. And then I gave another version to the INCOSE Requirements Working Group in the fall of 2019. And the question that was posed to me was, how can we or should we represent the requirements in model-based systems engineering? And their particular request was about non-functional requirements, but I try and avoid using that term because every time it comes up, people argue about what's functional versus non-functional. I had addressed primarily functional requirements at the lightning round presentation at the symposium in 2019. And as I said, that video is available on YouTube. For the INCOSE Requirements Working Group, I was focusing on non-functional types of requirements. The background for this presentation is the continuing problem of incomplete and ambiguous requirements and whether MBSE can help. And I've been working in requirements for 30 years, and it doesn't seem to get better, which is really disappointing. But there we are. So maybe if we get a new tool, maybe we can make things work better. I have included a number of references here, papers that I've done on structured requirements, requirements validation, the lightning round presentation on YouTube. If you can get into INCOSE Connect, then you can see a video of the original presentation. And a lot of this is based on a patent which was issued a few years ago. So I'm going to talk about different types of requirements and how we can use the architecture and model-based systems engineering to be able to generate different types of requirements. So I want to first talk about where do requirements come from, what do we mean by validated, then talk about basic requirement structure, different types of requirements and their associated structures, and the data elements that go into them. And that's really key to being able to move into, well, where can you find that information in the architecture? And then I'll move into an example discussion using an MBSE tool called CORE from the Vitek Corporation. Then talk about simulation for requirements validation and some other techniques and then how we drill down into the architecture to complete the design. And then we'll summarize at the end and take questions. So why do we want to do this? Well, we want to do this, or we should do this, because requirements should come after the analysis. It should not be the case that we simply write requirements and devolve into requirements at multiple levels. Rather, we should be analyzing from various stakeholders what the needs are, what the specific capabilities, what the solution characteristics must be, the measures of effectiveness, that's what I mean by MOE, with some analysis, and then derive requirements, and then drill down from the stakeholder level to the system level. What we want to do is avoid what often happens, which is we don't do any of this, or maybe we do it after the fact, and we just decompose requirements. Sometimes we do it by just changing the shall or changing the name of the system. And we've got a rich source of information available to actually develop good requirements. In fact, I say in here, derive and validate, not just simply trace to the parent requirement, but derive requirements by the analysis of functionality and interfaces and performance attributes. And that will generate the information we need to be able to write the requirements, derive the content. And if we do that consistently and in a disciplined manner, this should lead to better requirements compared with simply going from level to level in requirements decomposition without regard to the architecture. The MBSE world is primarily on the left. That's where the analysis and the architecture are. The requirements are part of that, but they are the result of doing the hard work of the architecture and analysis. We trace the requirements both to the architecture and analysis and to the parent requirement. And that's why we want to see how we can use the MBSE data to generate our requirements at each level. I was one of the reviewers of an earlier version said, you got to explain what you mean by validated. So I've synthesized one of the papers we did a couple of years ago with Bob Noel from the Boeing company on what we mean by validated requirements. We basically mean we have the correct set of correct requirements. You will find in the literature, you may see other terms. Commercial aviation industry uses correct and complete, but these terms are not disjoint, including in their guidance documents, because incompleteness is a form of incorrectness. So I've settled on correct set of correct requirements, meaning that each requirement is correct and the set of requirements is correct, meaning I only have correct requirements and I don't have any unnecessary requirements. Correctness inherently includes complete and implies to each individual requirement and the set of requirements. What we mean by correctness then is there's no missing information. I'm trying to get my slider over here. At first, we look at individual requirements, that there's no missing information. Each requirement has everything that is needed. And so we're looking that it is verifiable, meaning it is sufficiently clear and complete to be able to prove that it is needed, sufficient, and feasible. And those are the other characteristics. But if we can't understand it, or it doesn't have all the information, then these other things cannot be determined. So next we look at the content of the requirement, and we examine sufficiency by using analysis and simulation of function, timing, performance, information exchanges, interface connectivity, so that we can determine that if the requirement is implemented as stated, will it be sufficient to satisfy the parent requirement and need. And if information is missing or incorrect, then the requirement cannot be sufficient. So sufficiency addresses both types of incorrectness, the type 2 of no missing information, and the type 1, no erroneous information. And we went through this in the 2018 paper. If you'd like to get a hold of that, it's in the INCOSE Wiley library in the symposium materials. We examined necessity by ensuring proper derivation from a parent function. Can the parent requirement or need be satisfied without this requirement? And when in doubt, we can simply delete the function or alter the performance attribute in the model and assess the results. And in some cases, we can compare requirements on the system with the solution characteristics to establish feasibility for performance, sizing, reliability, and other parameters defined in the model. Can we obtain a solution that satisfies this and all other requirements within the program constraints and with acceptable risk? These 4 criteria are disjoint, concise, and complete. That is, necessary and sufficient to determine correct and complete, and therefore establish the correct set of correct requirements as the definition of validated requirements. And these 4 characteristics synthesize the 14 attributes of requirements that are included in the INCOSE Guide to Writing Requirements. The basic structure of any good requirement is the who, shall, what, how well, under what conditions. I first learned this in my system engineering career over 30 years ago, and a number of authors have taken credit for it. I can't actually tell you the source of it, but one of the things that's important is that by understanding and examining the structure, we can make progress on quality improvements and validation and so forth. This structure is partially captured in the INCOSE Guide to Writing Requirements and the associated ISO 29148, where they have this form: the subject, shall, action, verb clause, object clause, optional qualifying clause, when, condition clause. And this is all good. These are in the Guide to Writing Requirements, and there are in that guide additional examples, but there isn't a comprehensive list of standard templates to be considered. And this one only addresses functionality. And if somebody could go on mute, please, because somebody has an open microphone. There are multiple examples in the tables in the guide that reference different rules and describe good and bad requirements and acceptable versus unacceptable forms of requirements, but there actually isn't a comprehensive list of types and associated templates, and different tools have different approaches. There are some other papers that I reference in our 2015 paper that have addressed different requirements types, structures, and templates, and different tools implement some of these templates. And one of the reasons we have such a plethora of options is that these structures are not defined in SysML. We don't have a standard set of structures, and this particular structure from 29148 doesn't address the non-functional requirements like suitability, design, and environments. People may understand how to do functional requirements in MBSE, but can we also define such non-functional requirements and instantiate them in an MBSE tool? In particular, can we find the data elements in the architecture for not only the functional, but also the non-functional requirements? So the 4 types we developed while I was at Boeing. We tried to limit the number because we had to teach people how to use them, and even 4 ended up causing a degree of confusion. So let me quickly go through these. They are elaborated in detail in this paper. The functional performance type, which are mission-oriented characteristics, include interface requirements that address the inputs and outputs, And the reason for that is I continue to argue that if the function is not observable at the boundary, then it cannot be a good functional requirement at that level of the architecture. So that's why we always include a description of the output. And there's no separate functional type, as in the CBOK, unfortunately, System Engineering Body of Knowledge, and drafts of the latest guide from the Requirements Working Group. And I hope that gets changed, because a requirement without measurable performance is not verifiable, because you don't know the how well and you don't know how to determine the success or failure. Design requirements, which are constraints on the solution, things like parts, materials, processes, physical allocations, constraints on the interfaces like how to implement an interface and conformance to certain standards. The suitability type, which are non-mission specific characteristics that address fitness for use, like safety, different ilities, and different life cycle elements like transportation and storage. And then we have the environment requirements, which are primarily condition statements, but they have to be augmented to define, well, what do you want the system to do or be under these environmental conditions? And we might have different conditions for different operations or life cycle phases or different states and modes for specific functions. The first and most important thing is to define for your organization what structured requirements do you want to have? That is, what types of requirements do you want to have that implement this basic structure? And since there isn't a global standard for all different requirements types, and SysML does not yet have standard types because it doesn't break the requirements down into their data elements, your organization must define your specific templates to implement the basic structure for different types of requirements. So the answer is not yet in the tool. So the first thing is that process must lead tool implementation. So before you embark on doing this in MBSE, you must define your requirements types, structures, and individual data elements, and then figure out how to use the tools to implement them. You can't simply implement a tool. So these structures I'm going to show you grew out of our work at Boeing, where we defined 4 different requirements types and their associated structures and the data elements in the model. First, we have the very common functional performance type, which ends up being one of the longest type because it has the most data elements, and you can see the elements highlighted in green over on the right. The function, the interface output constraint, performance parameter for the function, timing if it's a triggered event, the trigger itself, and the input interface constraint for the trigger, and the more general condition statement. This type relates to mission-oriented functional performance. The design requirement type, the blue elements, has a design constraint with optional performance and optional condition, like dry weight or wet weight, for example. This type constrains the range of acceptable solutions. The environment requirement type, these are the tan elements on the right, identifies the particular characteristics of what the system must do or be, so that's the exhibit characteristic, during, after, or during and after exposure to some impressed environment with optional exposure duration for some period of time. And finally, the suitability type, these are the purple items on the right, which identify the characteristic, such as availability or reliability, a mandatory performance attribute, a mandatory condition statement, and an optional condition duration. So these are from our 2015 INCOSE paper and associated patent, and these are the ones that we used at Boeing to help us develop this idea of structured requirements and measuring requirements quality and so forth. So it's really up to the requirements engineer, the architect, and the organization to figure out how to realize the basic structure, the who, shall, what, how, well, under what conditions in a particular organization. And that's a necessary condition to be able to make progress in this area. Because the first thing is to get the process defined, and you need to know what the structured elements of the requirement are. So what I'm going to describe from here on is tool and implementation specific, which is why I emphasize that for you to do this in your organization, you have to first determine your organization requirements types, how many you're going to have, what their structures are, and then what their associated data elements are going to be. Once you have that, the next step is to map the requirements elements from your structured requirements types to the data model in your selected tool. This is a portion of the data model in Vitek's core tool, and this is what I use in my graduate class. These are some of the architecture classes that we use to construct elements of the requirements in model-based systems engineering. This is how we go about it and how I instruct the students, but virtually none of the students is using this tool. And so they will, one of the things they have to learn is how they're going to adapt the idea of the methodology and the data model to their own work back at their companies. So let me go through the elements of the basic structure then. The agent is the implementing element. So that's a noun. And in core, it's got two different data classes, depending on whether it's a operational perspective, where it's performer, or system perspective, where it's a component, because this tool, like many others that implement an architecture framework, has a different data model for the system versus the operational perspective. So we have two different classes to implement the same characteristic. These addressed who or what is doing it. The shall doesn't have a particular class. Your organization or sponsor may require a different word for mandatory characteristic. I'm hearing that must is intruding into this area, shall is going away. I always tell people, well, just define the mandatory word up front in your specification, and then it doesn't matter what the Supreme Court has to say about it. The next characteristic is the function. This is the observable action and the observable output, what the action is delivering at the system boundary. And this is why I argue for clear system boundaries and clear observable outputs. Otherwise, you're not going to be able to do verification well. This is one of the subjects we'll talk about in my tutorial on the June 19th. And there was information about that presented earlier. So in the operational perspective, we have operational activity and operational item. So that's the output. In system perspective, we have function and item. The interface constraint for the output is represented by an interface description, the need line in the operational perspective, and the link in the system perspective. So this is where you would call out, for example, a standard or an interface control document for implementing the constraint on the interface that transfers the output, that is the item or the operational item, from the operational activity or function. The performance attribute is not directly represented in the core data model. You won't find it anywhere in here. In core, I add a parameter as an attribute of the operational activity or function. In SysML, you can use a parametric diagram, and I'll show these later, but performance is not a separate class in core. So you've got to figure out how to represent those measurable attributes of the function. The conditions can arise from multiple things, so there's several classes that might be used. They may be associated with states. So we can use the state class from the state diagram. They may be associated with environments, which doesn't have a separate class, but can be represented as an input, as either an item or operational item, or by a continuous input condition while the system is doing something or receiving something. An event trigger is an input that initiates a function, and it is also represented as an item or an operational item, and that initiates an activity or function respectively. The event trigger has an interface input constraint, again represented by the need line in the operational perspective or the link in the system perspective to capture the interface constraint. The timing, which is a how fast performance attribute or with what kind of delay, is also an attribute of the operational activity or function, and I'll discuss this later. The design constraint was a challenge to figure out where that might be. It's a little harder to address. I'll get into that in more detail. But everything we're addressing, even constraints on the solution space, should arise from a user or other stakeholder measure of effectiveness or parametric diagram or some other capability, some concern, and it shouldn't just be levied willy-nilly out of the thin air, as we might say. Other characteristics are some attributes that represent what a system is, has, or does for the suitability and environment types. The function or the measure of effectiveness, or using the capability class as a measure of effectiveness, for example, for system availability, for the suitability and environment types. The environment exposure relates the input to the operational activity or function as during or during and after, and is represented as an operational item or item. It's an input. It's impressed upon the system. Finally, the exposure duration relates the characteristic to the input, and the duration can be modeled as an attribute of the operational item or item. So we have some of these requirement elements represented directly in the MBSE model as classes or data types, and some are represented as attributes on those classes. And now I'm going to go into these in more detail, but remember, these are specific to this tool. And if you're using one of the other tools that people mentioned during the introductions, you're going to have to figure out how you represent your kinds of requirements and their associated data elements with the data model of the tool you are using. And I'm hoping that sometime in the future, SysML will standardize this for us, but we're not there yet. So first, let me talk about the functional performance type. This is easily represented on the requirements diagram with the requirement. So this is a customized diagram I made in Core, and with the requirement itself and its associated function. So the requirement specifies the function, and using this diagram, we can go through the specific elements of this requirement type using the information that's available on the enhanced functional flow block diagram or an activity diagram, which captures the same kind of information. So the function is displayed with its title, description, and how it is instantiated in the flow, and how it is implemented in the requirement. And this implementation in the requirement in this tool is a manual transcription. The information is provided. We know what the function is, what its name is, what its description is, and some of the other characteristics, but it really is up to, in this methodology, the requirement engineer translating that into a valid requirement statement. And this is because Core and most MBSE tools don't parse the requirement into their respective data elements. And again, this capability isn't yet available in SysML. So it's up to the requirement engineer to faithfully transcribe the architecture information in the MBSE model into the requirement. And so this function addresses the what of the requirement. The interfaces include both the inputs and outputs. And in this diagram, I've added inputs and outputs onto the function description because that's a capability available in this tool. So the inputs include those items that trigger the activity or function, and they are represented on the EFFBD and partially address the under what conditions of the requirement. The outputs represent the observable result of the executing function, the what, and get transcribed into the requirement statement as that part of the requirement. The performance attributes are represented as parameters in the model, including the timing as a duration, so it's represented right here, and such things as accuracy and reliability for each function. And these address the how well of the function. The component enables a check on the consistency of allocation to the requirement and function, the who of the requirement. And this helps us avoid what we call level errors or misallocation. The condition element as a state is captured in the function and also in the requirement, in this case in the operating state. The result is that we get all the data necessary to populate the requirement template for the functional performance requirement type. The agent shall function in accordance with interface output with performance and timing upon event trigger in accordance with interface input while in condition. Now I want to go into a bit more detail on some of the requirement elements. Let's first look in more detail at the performance elements. In core, because there's no separate class for these, we've implemented these as parameter attributes on the functions, and these will be different depending on the tool you're using. We instantiate the specific parameter such as accuracy or reliability, and then this information is available on the requirement diagram as the requirement is being written to help ensure that we're not missing something. In addition to the user-defined parameters, Core also has a standard attribute called duration that can be used to represent timing in the function, the how well associated with the time between the observable input, the event trigger, and the observable output. These features are why you must be able to customize the modeling tool to capture the data elements associated with your requirement structures. And every tool is going to be different, and every organization will have a different set of requirements types and structures. And there's no universal standard as yet, and this is why you must begin with your process, requirements types, and requirement structures, and then you can adapt the selected tool to your process. Performance parameters can also be represented in the SysML parametric diagrams because here we're able to write equations and define outputs from these constraint blocks that can be used to instantiate the performance element in the requirement. And this is a standard capability in SysML, these parametric diagrams that can be used to directly capture performance information. And all SysML tools have a parametric diagram that can be used for this purpose. Condition statements, as I said, arise from several possible sources. They may be state conditions, and here we show a state diagram and the assignment of the function to the specific state. In this example, we want this function available during the operating state, so we capture this in the model and make the information available on the requirement diagram based on the function. We can also define subordinate states as we choose for more state granularity. Otherwise, we may choose to identify environments as conditions, environments are actually inputs into the functions, and here I've identified weather as an input to the system function. We treat the environment as a continuous input, and it will show up on the function in the requirements diagram when we're writing the requirement. Or if it's a time-limited function, it may be applied as a triggering event. This can also be applied to the environment requirement. We use this particular input item to capture the environment condition associated with this requirement template. And we can similarly apply an input environment as part of our condition statement for our functional performance requirement type. It wouldn't necessarily be a triggering event, but could be a continuous input. And if we want to limit the duration of a particular input, we can add exposure duration as a parameter on the input, in this case, on the weather input. Then we specify the exposure duration for each of the various environments like humidity, vibration, temperature, and so forth. But we can instantiate that information on the input. Again, this is peculiar to your specific MBSE tool. So we can use the MBSE tool to implement the various data elements of the several structured requirements templates. And I'm not claiming this is universal, because you have to apply your process, your requirements data structure with your selected tool to be able to figure out how this is going to work. So you have to analyze your tool to get that to happen. For the design requirements, there's a lot more, there's less specificity about exactly how to go about this. So we think about, well, what are the design requirements actually specified? The reality is that many design requirements are poorly justified and seem to pop up without much precedence or traceability, simply as solution preferences rather than actual requirements. So the first thing is to get rid of those that are merely solution preferences. But they might arise, for example, from concerns, which can be captured in the architecture, or they might arise from measures of effectiveness, such as system availability or reliability or safety. These can get decomposed and translated into specific design characteristics, as well as other kinds of requirements. And whenever we use a design requirement, like all other types, it's important that we maintain traceability to the source so that we can understand why we have this requirement, rather than simply specifying a preferred solution with no justification. We sometimes use design requirements as shortcuts for lessons learned in resolving certain issues. For example, rather than requiring extensive testing, we simply require the use of certain materials or processes based on suitability criteria and environments because, based on our research, we've determined that such a solution will enable adequate reliability and performance in the specified environment. And we sometimes derive design requirements as an allocation from a functional decomposition. For example, fuel capacity could be derived from mission performance requirements. We don't specify a particular function, just the size of the fuel capacity and a physical characteristic. That's not the only way to do it, but it's convenient and sometimes simpler to verify compared with alternative requirements. And we sometimes derive requirements for particular parts, materials, and processes based on reliability, maintainability, interchangeability, or cost considerations. Again, the specification of the solution is a shortcut to achieve a measure of effectiveness or satisfy a concern. And this form can save programmatic funds compared with performance testing and analysis. And it's important that we are clear in the MBSE environment what the source of the requirement is, whether a concern, a measure of effectiveness, or some other parent requirement or need. We may have design requirements that arise from budgeting, such as space and weight and power and cooling, and reliability. Although reliability is more of a suitability criterion, it has to go through a similar budgeting process in the allocations. These derived parameters can be captured either as a parameter on a function for reliability, for example, or as a parameter on the solution component as well. It could also be captured from a parametric diagram based on a decomposition analysis of a functional requirement that yields not only derived functions and performance, but also design constraints like fuel capacity or weight as next lower level requirements. Interface requirements are typically going to be identified with the associated functional performance requirements for inputs and outputs. And in the Boeing templates I showed you, there's no separate interface requirement type because such requirements are either about the inputs and outputs associated with the functionality or their design constraints associated with how the interface is going to be implemented. And in the functional case, these can be referenced to interface control documents from within the functional performance requirement, thus constraining the range of allowable solutions. As design constraints, these can be stated explicitly or by reference to a standard to achieve, for example, some degree of interoperability as a concern or measure of effectiveness. The suitability characteristic may have an attribute about our system of interest that it is something or has something or does something, like it has an availability, and we can capture that availability as a parameter traceable from a measure of effectiveness at the operational or system level with the attendant numbers provided. The characteristic for environments may be a statement about, for example, reliability under exposure to specified environments and durations. It is important to be clear in these environment requirements regarding what is the mandatory characteristic to be exhibited during and or after environmental exposure. These need to be verifiable, specifying some observable is, has, or does something. Ambiguous words like survive exposure to a particular environment are not specific enough so that we could actually prove compliance, because there are many possible interpretations of a word like survive. So phrases like shall operate with measured reliability that is defined somewhere, or satisfy all requirements defined in a particular section must be verifiable. We can use the condition statement to help us focus on what we must have during and or after exposure to the particular environment. And such thinking can help us clarify the characteristic. On this slide is an example calling out functionality during exposure to environments. In this case, I'm identifying the specific functionality, all per section 1, and the associated conditions per section 3 defined in the specification with the specified operational environments, such as weather, as the input condition. And I've seen people get very nervous when they see a statement like this and wonder if they must test every functional requirement in every combination of environments. The obvious answer is no. Not all conditions must be tested for each and every function, and that would be sorted out in the verification requirement. But it does mean that every functional requirement must be satisfied while the system is operating in such an environment. It certainly cannot be allowed to fail to perform the required function with the requisite performance. The verification of this, which functional requirements will be examined for which combinations of environment, would be specified in the verification requirement as a subset of all possible conditions. So these are ways of addressing the characteristics in the model. They trace to input conditions, functions that are identified, and the source measures of effectiveness. A very important means to validate a requirement is by simulation. The other means that I've shown you is you actually derive the requirement from the source information, the measures of effectiveness, the functional analysis, the associated performance analysis, so that the numbers captured in the requirement are truly derived from the engineering analysis. But another way is to simulate the architecture to validate the model for logic, control logic, timing, connectivity, input-output information exchanges, and parametric performance related to functionality and throughput on the defined interfaces. And which of these you can do depends on the capability of the specific architecting tool and any related simulation tools. We actually don't simulate the requirements themselves, and this is key. We simulate the architecture behind the requirements. So in this case, the enhanced functional flow block diagram with the functions and the inputs and the outputs and the associated timing and the control logic, the branching, the loopbacks, and so forth. The architecture model enables us to validate the requirements resulting therefrom because we can check for verifiability using the template and criteria. Are all the necessary elements of the requirements present and adequate? That is, the requirements data elements. A measure of individual requirements completeness. Check for sufficiency using the simulation of timing, performance, information exchange, interface connectivity. If the requirement is implemented as stated, will it enable the system to satisfy the parent requirement and need? Check for necessity by ensuring proper derivation from a parent function. Can the parent function or need, can the parent requirement or need be satisfied without this requirement? And when in doubt, we can simply delete the function or alter the performance attributes in the model and assess the model performance. And in some cases, we can compare requirements on the components with the solution characteristics to establish feasibility for performance, sizing, reliability, and other parameters defined in the model. Can we obtain a solution that satisfies this and all other requirements within the program constraints and with acceptable risk? And that's always a key question. We must be able to answer these questions to ensure validation of the requirements, and the architecture model can help. If we can derive requirements from validated needs and measures of effectiveness, then there should be no unnecessary requirements. Because we can check for sorry, I lost my place. There should be no unnecessary requirements by this process. So we can save ourselves the extra work, that is rework, if we follow this process. Sorry for that goof. As I conclude then, I want to emphasize the critical importance of doing the justifying analysis before attempting to write the requirements. It seems that we often get this reversed and we end up not being able to justify our requirements, or ending up with unnecessary or incorrect ones, or requirements that can't be traced to anything. And this can be made more difficult if our organizational workforce is separated into systems engineers that do modeling and analysis versus systems engineers that develop and manage requirements. And I don't advocate for that separation, because I think all good systems engineers should be able to analyze the system they're working on and do this kind of architecture and analysis. Then we'll have higher confidence that the requirements they're deriving are actually valid. Once we substantiate our requirements at the top level based on mandatory measurable characteristics and constraints, then we can decompose the logical architecture to identify interfaces, derive and allocate functionality, and the associated performance. This becomes a recursive activity to successively lower levels of the architecture. And note that traceability is inherent in this process because we know from where a requirement was derived because it arises from the architecture and the associated analysis, the function, the performance, the component, and the interface, which itself was derived in response to the parent requirement at the next higher level. In summary, then, let me emphasize again that this is process first. That is, if you don't have requirements templates, that is structured requirements of whatever types with defined elements for your organization, then you're going to need to decide which you're going to have, how many, what types, and what structure they are each going to have to be able to implement the basic structure of the who, shall, what, how well, under what conditions for the mandatory criteria. It may be that this basic structure is good enough for what you want to do, and you decide no further templates are required in your organization. And that's a means of balancing complexity with specificity in achieving your organizational goals for model-based verifiable requirements, but you're still going to have to figure out how to adapt the data elements in the modeling tool to your selected requirement elements of the who, shall, what, how well, under what conditions. Once these things are decided, then you can select and adapt a tool, process first, so that you can define the representation of those requirement elements in the data model of your selected tool. And having done that, you need to define the process then for establishing the relationships within the tool for the different data model elements and the requirements themselves, so they're available and visible and linked within the tool in the right places, so that you can be confident that the requirements you're writing are actually derived from that MBSE model data. And as I said, we don't yet have standards that are sufficiently mature so that we can say, well, we're using SysML and therefore we can instantiate a requirement of this type because all the data model elements for that type automatically feed into it. We don't have that yet. That's my wish for the future. It's certainly something to push for in future SysML versions, but for now, this is a manual process. Although I'm learning that some MBSE tools have established structured requirements and linked those requirements data elements to their architecture models, but it's not universal and it's not standardized in SysML. So for most folks, this is going to be a manual process, beginning with the process definition, including requirements types and structure, then select and adapt the tool. And for those of you that have tools first, and then you're going to now attempt to figure out your structured requirements, well, it's going to be harder because now you may be stuck organizationally with a tool that maybe doesn't easily support your structured requirements that you're wanting to have. And I don't have an easy answer for you other than, well, you may have to do more customization than you would like to do. Finally, I just want to urge you that develop requirements from concerns, measures of effectiveness, those various sources that are available in the architecture, stakeholder concerns, their MOEs, what are the concepts of operations and maintenance and testing? What are the system missions? What are the functions that are derived from all these things? What are the associated inputs and outputs, the conditions, the trigger events? What are the associated performance attributes? And then we have to relate these requirements elements to the source data, the MBSE architecture elements. So emphasize, start with the process, start with the needs, and figure out your requirements, your structures of requirements, then get this information into your selected tool and make the relationships so that you can write verifiable requirements. So I thank you very much for your attention, and we've got time to take questions. So
thank you, Ron, for an eloquent presentation, and we have learned a great deal. And I will start the Q&A with the first question in the chat.
okay.
Do we want the requirement elements to be defined at the system level or the element level?
I view there's no difference, that requirements should be the same at all levels. And if you'd like to engage further on that, you can come to the tutorial on the 19th. We'll talk about that in some detail. So you have a standard requirement type or a set of types that have a set of data elements that should be applicable at all levels. If you want to have different requirements elements or different requirements at different architecture levels, I think you're in trouble already. So I would urge you to revisit that decision. Because if it's a verifiable requirement, then it needs to have the who, shall, what, how, well, under what conditions. And if it doesn't have all those things, then it's probably an incomplete requirement. And the fact that you can't fill out the data at some levels means you now know you're missing architecture information. But if you come to the tutorial, we can talk some more about that. But we always used one form of the structured requirement at all architecture levels, because if it's a requirement, it has to be verifiable. That's the short answer. So sorry if I didn't satisfy that one. Next.
Next question, Ron. Is this model available for Cameo as well?
Which model? The structured requirements that I showed you can be used in any tool. The specific adaptation will depend on the data elements within Cameo, and I'm not familiar with that. So you would have to go through a process similar to what I showed you for core, which is, okay, here are the data elements I have in my structured requirements, and here are the data elements or classes and attributes that I have in my MBSE tool. What's the mapping? And you've got to come up with the mapping. So you need an organizational MBSE data architect to do that mapping. So I don't know what the answer is for Cameo. I don't even know what the answer is for SysML in general. So that's one of the first things you have to be able to do. And unfortunately, we're behind on doing this because as a discipline, we have not recognized early enough that requirements have structure and they have pieces to them. And so these automated tools need to be able to represent those pieces and structures. Maybe we'll get there, but I don't think we're there yet. So I don't know what the answer is for Cameo or any of the other tools. Sorry about that. Next question.
Thank you, Ron. Is there an ongoing effort to standardize these structures and templates and to make them available in SysML version 2?
As far as I know, the answer is no. I had urged that upon the SysML 2 development, and I don't think it made it into it. So it's a disappointment, but it is what it is. So if you wanted to do this in SysML, and I know, I believe Boeing is doing some of this in their implementation, according to people I've talked with, you have to customize how you're going to go about it, because SysML doesn't have standard structured requirements. It just has a monolithic requirement and a requirement diagram, unfortunately.
Thank you. Next question. What is your definition of validated requirements? The requirements that are analyzed before and reviewed by different stakeholders?
Well, that would be one of the steps along the way. I found that review is insufficient. So a valid requirement is one where you have high confidence by analysis that if the system actually does what the requirement says, it will satisfy the parent need. If you don't have that, then you haven't yet validated the requirement. There's lots of things that can go into increasing your confidence in that. Review is woefully inadequate to that job. So by itself, I would say review has a high likelihood of failing to actually validate a requirement. Certainly it's better than nothing, but reviews I've observed, the primary goal is to finish the review, book the requirement, get it baselined, and issue the specification. And then we'll sort out all the errors and incompletes later. And that's a sad reality. So if you don't demand evidence, like show me why this is the correct requirement for this element of the system and why it's necessary and sufficient to satisfy the parent requirement and need, and why it's feasible with respect to the program from the perspective of risk and schedule, which is why we have those 4 validation elements of verifiable, so we can make sure we have all the structural elements, and that necessary and sufficient, and then feasibility. And I'm planning to give a chapter talk in 2 weeks to the Seattle chapter, going through some of the history of how we arrived at these structured requirements and these ideas of necessary and sufficient, going back to my first INCOSE paper in 1995. So if you want to dial into the Seattle chapter meeting 2 weeks from tomorrow, you'd be more than welcome. So hopefully that'll get posted in INCOSE events.
Thank you. Next question. You talked about analyzing requirements. Is there any math involved in performing this analysis?
I hope so. If there's no math involved, then you're probably missing performance as an attribute. So it's got to be more than, oh, that looks like a nice function, or I decompose the function into these other functions. We use math in the form of set theory to make sure that the union of the sets of functions actually produces the parent function, for example. And we use arithmetic to ensure that when we add up all the series times in the decomposed requirements, we can meet the parent timing requirement. I recall a project I worked on, and we had a very complicated in-process test, operational test that we had to do, and we had 2 minutes to do the whole thing over 1,000 pieces of equipment. So that didn't happen willy-nilly. It happened because we had a very detailed functional sequence with allowable times, lots of parallelism, and we had to prove by analysis that it would actually work. And then we also had to prove when we actually built it that it actually worked. But we didn't build it until we were sure that we had the right times and the right sequences. So yes, math is involved.
Thank you. Next question. How do you think that constraints from downstream 15288 processes such as implementation, integration, and verification flow back into this kind of approach? For example, an architectural decision to make verification easier, such as for verification deciding to push an externally exposed timing signal on an unused pin to verify CPU usage.
Well, like all things in the design, if you don't get it in up front, then you end up with rework. So when we talk about developing concerns and measures of effectiveness, we always are supposed to consider various life cycle phases. It's not just about operations, it's about maintenance, and it's also got to be about verification, including testing. So yeah, this is a common conundrum, because the folks writing the requirements don't necessarily think to ask the people who are verifying the system. Integrated product teams were supposed to help with that. And initially they did, because we had people from verification involved in defining the requirements and people from manufacturing. But it may be that integrated product teams became functional teams, and we sort of lost the ability to influence the requirements and design from the other life cycle phases. So absolutely they need to be involved, because you got to collect up the requirements based on how are you going to do your verification, and how are you going to do your maintenance, and how are you going to operate, and how are you going to dispose of the system. And if we fail to address those as concepts of early on, we are likely to miss requirements. One of the benefits of using an architecting tool is you can put that stuff in the architecting tool. And you may not have all the details to start, but you've got a placeholder to capture it, and you can start detailing it out. And before you say you've finished the requirements, you can say, you know, have we really got everything associated with these other life cycle phases? I insist that my grad students do that in their design projects. They have to do maintenance and show me how they're going to do maintenance in their model-based requirements and in their architecture models. So it can be done, but it does require organizational discipline and perhaps organizational structures to enable that to happen.
Thank you, Ron. Next question. Do you have any thoughts on how to use MBSE to define or analyze verification requirements? Is there a kind of structure to a verification requirement that can lend itself to this kind of approach?
Yes, as a matter of fact. So I teach my grad students a 3-part model that I learned while we were at Boeing. So you can represent those elements, and whether it's 3 parts or 4 parts or 2 parts or whatever the elements are, like, you know, so core and other tools has the ability to select, well, what's the verification method? So that becomes part of it. So you select that, that's built into the tool. So I just click the method I want. You need to define the conditions under which the verification is going to happen. It's going to be some subset of throughout the flight envelope, for example. So you have to define that, and that can be captured in the tool. You have to define the success criteria. Well, much of the success criteria are already defined in the MBSE model when you've got the performance attributes and the function and the timing and so forth. So you may have some of that information already. And if you want to have a different structure of the verification requirements, then similarly to how we define the structured requirements, you have to figure out, well, what structure do I have? Do I want to use? And where am I going to capture the data for that in my MBSE model? And again, it will depend on the specific MBSE tool that you have. But yes, you can definitely do that.
Thank you. Next question. Is it possible to feed doors requirements as input to architecture, to the architecture tool, instead of creating new requirements in the tool itself?
Yeah, but yes, and it comes with a lot of risk. If you have the idea of feeding a completed requirement into the architecture, then you're kind of going backward at any level. If you start over here and you go left, then you're deriving requirements the wrong direction. One of the tool developments we did with doors, we actually implemented structured requirements in doors, although we didn't have them linked to the architecture because we weren't that far along. So the elements of the requirements in doors were already associated with the structured requirements I showed you earlier. So if we had made an association of architecture to the structured requirements elements in doors, then we would have exported the architecture data from the architecture tool into doors, not go the other way, because the requirements are a result of doing the architecting, not the source of the architecting.
Thank you. Daniel Durkin, are you still on the line? Would you please unmute?
Yeah, hi, I'm here. Sorry,
Would you please
that's
ask your question about conditions? It seems to be quite a long, lengthy question.
Yeah, sorry about that. I have a lot of questions. So a question I had for you is with states and modes kinds of requirements. I followed what you were saying about the conditions, but I found that in traditional specs, usually the states and modes section talks about how states are triggered.
Yeah.
And then like the capabilities sections generally reference the states and say like in this state, this function should be available and stuff. Okay. So with that said, do you see those as kind of being separate, the requirements around how to transition into and out of states versus which functions are available in each state? Or are they separate types of requirements, or are you proposing that they'd be like one set of requirements?
Well, they would be formed differently. An event that triggers a change in a different state would be written as a triggered functional requirement. Whether the requirement actually, I mean, there would be no need for the requirement to state that upon this trigger, transition into this state. Well, that's not very meaningful from a verifiability perspective. That's not really observable. So we use states in a couple of different ways. One is to attempt to manage transitions. But the reason we attempt to do that is because we have these buckets of functionality that we may call states to say, we want to be able to do these sorts of things in this state. So we need to know what particular events get us into that. And the very first event that does that is going to have some observable functional performance requirement associated with it, as well as a information in the architecture that says, oh, in the state diagram, that kicks us into this state. But that first function is one of dozens, perhaps, of functional requirements that are available in that state. So I hope I'm answering your question. I don't necessarily view them as two different kinds of requirements. A requirement that says the system shall have an operating state is absolutely useless. And I would never have something like that. Yeah. If you had a section that said, that here are the transitions, well, those can be represented in the architecture tool. But again, they don't have to have a shall in the requirements document. It's just descriptive information.
Yep, I agree with what you said. It just, people typically, they're for some reason afraid of words and afraid of repetition and requirements. So there's the natural kind of inclination to try to reduce the redundancy of statements. And I'm just curious to see what your thought was on that. Thanks.
Well, and I've seen the problem of if you fail to put a state definition in a requirement, sometimes it doesn't happen in the proper state, or worse, it can happen when it never should. And that can be a real problem. So the practice of identifying the applicable states for requirement is something that should be considered, especially for a function that is supposed to be limited to, like, it only happens on the ground. For an airplane, it should never happen when you're above the ground. Well, that should be stated that way. It can only happen in the ground state. And then it has to be proved, because if it happens in the air, it can kill people. And I know an example that I won't talk about right now, but it was in the news 30 years ago. It was a very tragic accident, but it was because a lack of state definition on a requirement.
Yep. I concur. Thank you.
Okay.
It is 7:32.
Mhm.
And I believe that we probably should stop the recording at this point
Okay.
and thank